Welcome. Today is Thunder Thursday, December 2, 2021. Thunder Thursday. Today we will prove that the neutronium inside a neutron star is at 300 trillion Adoni Kelvin degrees below absolute zero. Now, the first hurdle we have to overcome is physicists believe you cannot have temperatures below absolute zero. And that is true for matter particles, okay? If a matter particle that's at matter density, okay, it's going to emit electromagnetic waves. For instance, if we compact hydrogen atoms, if we compact them to a solid, we can compact hydrogen atoms to a solid, and that solid would be at 14 degrees Kelvin, and it will emit a certain electromagnetic wave because the proton sacks and the electron sacks, they hover and pulsate, okay? So what they're pulsating is God particle 1s. We define the God particle 1 as the smallest particle of mass in the universe, and that it's of Planck length or lower. I got a burping fit. I don't know if I should start over or not. But let me continue. Excuse me for burping. This is going to be more of a burping video than a proven video. Anyway, well, the burp has pressure. Let's use the burp to prove our thing. There's pressure inside, and that pressure is harmonized from many different atoms. And then it's also harmonized, the pressure is also harmonized from the atoms are pulsating, and then I got stuff fermenting, and that makes gases in my stomach, and I burp, okay? Now going into this burping discussion, it's not going to help me prove that there are temperatures below absolute zero. So let's move over to what we got for proof. Okay? So if there are no electromagnetic waves coming from a mass, then they say that black body with no electromagnetic waves coming out is at absolute zero. And the closest they can get to absolute zero is the event horizon of a black hole. Okay, now what physicists say happens at the event horizon is that the massless photon doesn't have enough velocity to overcome the gravity of the black hole, okay? Now, what I say is, since I'm Adoni and Adoni says, because I'm Adoni the physics guy, what Adoni says is that a massless photon cannot be pulled into a black hole, and it cannot be kept into a black hole, okay? Now, we are given that massless photons carry momentum. Well, a massless thing cannot have momentum. A massless particle cannot have momentum. Only a matter particle with mass can have momentum. Therefore, since electromagnetic waves are waves, just like sound waves are waves in air, and they have all the attributes of sound waves. They have Doppler effect, they have harmonics, they have constructive and destructive interference, just like sound waves. Then we can conclude that the electromagnetic waves propagate in a medium of God particle ones, and that this medium of these tiny, tiny particles, okay, this medium results in the compression and decompression of the particles, and the atomic level compressions and decompressions harmonize into the electromagnetic wave. Now, at the same time that like the Earth gives up electromagnetic waves, it's also generating gravity. The reason it's generating gravity is because more GP1s are being compressed inside the mass energy vessels of protons, neutrons, atoms, electrons, and neutrinos. So when you net compress GP1s inside nucleon sacs, okay, they're permeable, okay, so they're continually pulsating, and if the outside pressure is greater, if the pump pressure is greater than the vacuum pressure, then more GP1s get compressed in. GP1s make up the structure of space. The GP1s are at a certain universe pressure. The universe, we know from the cosmic microwave background radiation, since the GP1s compress and decompress 160.3 billion times a second. Okay, that's the microwave background radiation by one measure, the highest frequency. Another one is 280.2 gigahertz a second, computed by a different way. Anyway, the universe, let's touch on the Big Bang Theory, okay? There are only four sacks. There are only four sacks that can permanently hold both mass and energy. They're the neutron sac, permeable sac, the proton permeable sac, the electron permeable sac, and the neutrino permeable sac. All those three sacs, only those four sacs, can permanently hold both mass and energy. And what I say, the potential energy inside a proton sac is compressed GP1. So many GP1s got pumped inside, and that's what makes the mass of the proton. Now, when an antiproton and a proton meet, they're spinning, they rip their sacs apart, and you get gamma waves, because all the compressed energy inside the sacs pulsates out quickly. Okay, so now all that is reasonable. So you can believe something reasonable about matter and antimatter and sacs ripping, and it has a physical explanation of how protons and antiprotons annihilate each other. Or you can go with the physicists that say, we don't know what happens, okay? So you can believe a reasonable physical explanation, okay? The compressed energy inside a proton sac is stored in the form of compressed God particle ones. And those sacks are indestructible because they're minted. They're minted inside neutron stars. So the way to think of the neutronium in a neutron star or the neutronium inside a black hole is as embryonic neutrons, okay? Now, a black hole does not evaporate by giving off energy. A black hole is at minus the neutronium in the black hole, the singularity in the black hole, the neutronium ball inside the black hole that can reach up to a mass of 100 billion solar masses. That neutronium ball inside a black hole is composed of embryonic neutrons. And when those neutrons get pumped up with GP1s to absolute zero, then they'll decay into hydrogen. That's how the universe gets its supply of hydrogen, regenerates itself. It does it by pumping up the embryonic neutrons inside the neutronium, okay? And there may be some neutronium inside white dwarfs, okay? Now, white dwarfs, they have a density from about 200,000 times Earth density to 2 million times Earth density. As you get closer to 1.41 solar masses of white dwarf material, the white dwarf shrinks and it gets to a density of about 2 million times Earth density before it explodes. Okay, you can check on that by looking up the smallest of the large. Well, it's the tiniest white dwarf, and also the most massive white dwarf found at 1.35 solar masses. So I'm losing my voice. My burping fit is over, but I still want to get. Okay, I want to get back to this solid hydrogen. Okay, solid hydrogen is at 14 Kelvin and has a density of 0.076 grams per cubic centimeter. Okay, that's a very low density. The Earth has a density of 5.51 grams per cubic centimeter, and as a multiple, well, I figured out what the multiple is, but I didn't write it down. Oh, it's 65 times. So if you multiply the density of solid hydrogen 65 times, you get to the density of Earth. Okay. Well, what that means is the neutronium in a neutron star is given as 100 trillion times Earth density. We're given that a teaspoon of neutronium is equal to 5.5 billion metric tons. 1 teaspoon, okay? That's very hard to grasp. I've repeated that hundreds of times, and it's still a mouthful, okay? That in the volume of a teaspoon, 5 milliliters, in 5 milliliters in the volume of a teaspoon, neutronium in a neutron star contains 5.5 billion, or is it 5 1.5452 billion metric tons. Okay, that's a lot. Okay, now I bring this up because another way to measure. Okay, now the only way you can get a neutron star to that density is through the Siemens refrigeration process. Okay, so how they get to solid hydrogen, okay? They compress hydrogen, but you can't just keep compressing because your compressor will blow up. Okay, you have to compress hydrogen. You have to take heat out of it. It has to be strokes. It's the Siemens refrigeration process. Compression heats up, remove the heat, decompression cools, and it gets denser. You keep repeating this. So our sun does this for 10 billion years, and it gets a white dwarf at about half the density of the sun. Now you get a slightly higher star, more than 10 solar masses, and you'll end up with a neutron star. So because the pressure is greater. So the point I'm getting here is solid hydrogen is at 14 Kelvin, which is not far from absolute zero. And it's not very dense. Okay, and hydrogen is basically a proton, which is basically a neutron. Okay. But the neutronium in a neutron star is going to be 6.5 quadrillion times more dense than the solid hydrogen at 14 degrees. What that means is the movement, the area in which a solid hydrogen atom could move, the area, okay? That area is going to be compressed to less than a femtometer cube, okay? So it's going to be very, very dense. It's the freedom of movement, okay? So even if we get hydrogen to absolute zero, and you take the heat out of it, so that the protons in hydrogen, you take the heat out of it so that the protons don't pulsate at an observable frequency. So the way you got it to solid hydrogen was you extracted heat. Okay? What I'm saying is to get it to 6.5 quadrillion times the density of solid hydrogen, okay? Because neutronium is just protons. And they're 6.5 quadrillion times more dense than solid hydrogen. What I'm saying is I forget the word, I don't know if it'll come to me, neutropy, the neutropy, the neutropy of solid hydrogen is much, much greater than the neutropy, the freedom of movement of the neutronium in a neutron star because of the increased density. So when you increase the density, you generally decrease the temperature. And in order to get hydrogen to neutronium, you have to compress it 6.5 quadrillion times. And in order to do that, you have to extract a lot of heat. So when you warm up the neutronium, the embryonic neutrons, the generated neutrons in neutronium, when you warm them back up to absolute zero, then you end up with a neutron. And then the neutron decays into a hydrogen atom. So that's how the world keeps getting, the universe, that's how the universe keeps getting resupplied with indestructible neutronium, indestructible neutrons that decay to indestructible protons and indestructible electrons, okay? You can't pull an indestructible proton, you can't pull it out of vacuum. And you can't pull an indestructible electron out of vacuum, okay? Now you can blow up an electron to a muon, okay? You send laser waves at it, intense laser beam, and the electrons will change to muons, okay? I have a whole video coming up on that, okay? So I lost my voice. It's got to be the craziest video that I'm going to publish yet. Talk more later. Bye.